Okay, so what I'm going to be going over in this lecture is S-domain circuit analysis for a particular circuit. So that circuit looks like this. And so this is the circuit that I'll be analyzing here. And the objective is to find the open circuit voltage at VA by converting from the time domain to the S domain and then back into the time domain to get the time domain expression for VA. So first I'm going to start off by assigning current directions, and this is the current directions that I chose for this particular circuit. The element S domain representation, so 20 U of t is going to be represented as 20 over S, and going back to the schematic here, I have this 20 volts, but it's only going to turn on at time 0, so that's why I have this singularity function here, U of t, which is going to make it 20 over S when it's converted into the S domain. R1 is going to be R1, R2 is going to be R2, ZC of S is going to be 1 over SC. That's the passive element of the capacitor model. VC of t sub 0 is going to be VC of t sub 0 divided by S. That is the active element of the capacitor model in the S domain. And then Vx over 5 is going to be Vx over 5. So the S domain circuit is going to look like this. The only difference here is that I put in Vc of t sub 0 divided by S here, okay? And the orientation is according to where the positive voltage is at. So if you're saying that the voltage is more positive at this node than at that node, then you orient your Vc of t sub 0 divided by S in this way, with the positive node going in that direction. Okay, so that's how you set that up. And so next, the current distribution at Vx. So starting the analysis here, I1 equals I2 plus I3. Let's go back to the schematic. I1 equals I2 plus I3. Okay, that's a current distribution law. Okay, so note that at node VA, I3 plus I2 equals 0. So let's go back to the schematic. I2 going this way plus I3 going this way equals what? Whatever's coming out of here. Well, this is an open circuit, an open voltage circuit here. Okay, VA is open, so apparently that current is 0. So that's where I get I3 plus I2 equals 0. And so it follows that I1, which equals I2 plus I3, also equals 0. And so now we have I1 equals 0. Then I decompose I1 into 20 over S minus Vx divided by R1 equals 0. Okay, and then next 20 over S minus Vx equals 0. And then next I have 20 over S equals Vx, and I am making that equation number 1. So voltage distribution at the closed loop. So what loop am I talking about? I'll go back to the schematic here. I'm talking about this loop here. So that's where I'm analyzing it now. So at that closed loop, I have Vx divided by 5 plus Vc of t sub 0 divided by S plus Vc of S equals Vr2 of S. And so then that now becomes Vx over 5 plus Vc of t sub 0 divided by S plus I3 times Zc of S equals Vr2 of S. Next, that becomes Vx divided by 5 plus Vc of t sub 0 divided by S equals I2 times R2 minus I3 times Zc of S. And then make a note that I3 equals negative I2, because remember we had I3 plus I2 equals 0 right there. Okay, so that means that what? I3 equals negative I2 from that. Okay, so next we have Vx over 5 plus Vc of t sub 0 divided by S equals I2 times R2 plus I2 times Zc of S. And so now we have Vx divided by 5 plus Vc of t sub 0 divided by S equals I2 times R2 plus 1 over Sc. Next, Vx divided by 5 plus Vc of t sub 0 divided by S equals I2 times R2 plus 1 over Sc. Next, we have Vx over 5 plus Vc of t sub 0 divided by S equals I2 times SCR2 plus 1 divided by Sc. Next, we have Vx divided by 5 plus Vc of t sub 0 divided by S, all of that times Sc divided by SCR2 plus 1 equals I2, and I call that equation 2. So now I'm going to combine equations. I'm going to take equation 1 and put it into equation 2. That gives me 20 divided by S, all of that divided by 5, plus Vc of t sub 0 divided by S, all of that times Sc divided by SCR2 plus 1 equals I2. And then 20 over 5S plus Vc of t sub 0 over S, all of that times Sc divided by SCR2 plus 1 equals I2. Next, I have 4 over S plus Vc of t sub 0 divided by S, all of that times Sc divided by SCR2 plus 1 equals I2. Next, I have, by adding these two terms here, I have 4 plus Vc of t sub 0, and I have a cancellation here, and so that makes it 4 plus Vc of t sub 0 times C divided by SCR2 plus 1 equals I2. And then for equation 3, I finally get 4 plus Vc of t sub 0, all of that times C divided by SCR2 plus 1. That's equation 3. So now I have VA. Now, what about voltage distribution at VA? Well, VA equals Vx plus Vx over 5 minus VR2 of S. And so VA equals Vx times 1 plus 1 over 5 minus I2 R2. Next, I have VA equals 6 times Vx over 5 minus I2 R2. And that is equation 4. Okay, so now I'm going to combine some equations. I'm going to take equation 3 and I'm going to put it into equation 4. That gives me for VA that VA equals 6 Vx divided by 5 minus 4 plus Vc of t sub 0 times C, all of that divided by SCR2 plus 1, all of that times R2. And then next I'm going to take equation 1 and put it into equation 4. That gives me VA equals 6 times 20 over S, all of that divided by 5 minus 4 plus Vc of t sub 0, all of that times C, and all of that divided by SCR2 plus 1, and all of that multiplied by R2. Now I have VA equals 24 over S minus 4 plus Vc of t sub 0, all of that times R2C, and then all of that divided by SCR2 plus 1. Now I'm going to start simplifying some more, and so R2 is equal to 1 in this circuit problem, and C is equal to 1 over 2. Okay, half of a farad and then 1 ohm for the resistor number 2. So VA is now equal to 24 over S minus 1 over 2 times 4 plus Vc of t sub 0, all of that divided by S times 1 over 2 plus 1. And now VA is equal to 24 over S minus 1 over 2 times 4 plus VC of T sub 0, all of that divided by 1 over 2 times S plus 2. And then finally now we have VA equals 24 over S minus 4 plus VC of T sub 0, all of that divided by S plus 2, and that is equation 5. So now I'm going to convert equation 5 to the time domain, and what I have is 24 over S, just that part there. The 24 over S converts to 24 U of T. Then next, the other part, the other term, is negative 4 plus VC of T sub 0, all of that divided by S plus 2, which is here in equation 5. I'm going to now convert that, and that converts into negative 4 plus VC of T sub 0, all of that times e to the negative 2t. And I'm going to append U of T to this expression since the source envelope is U of T. Now, again, with these conversions here, if you look into any circuit theory textbook that covers Laplace transforms, they will have this information there for you for the conversions. So that is where I'm getting this from as a reference. Okay, so next, that becomes this part here that I was previously talking about. That becomes negative 4 plus VC of T sub 0, all of that multiplied by e to the negative 2t, all of that now multiplied by U of T, because I'm appending U of T since the source envelope is U of T. So now I'm going to put all of that together in the time domain, and the final expression for VA is VA equals 24 minus, in parentheses, 4 plus VC of T sub 0 multiplied by e to the negative 2t, and then all of that multiplied by U of T. Now the voltage plot, well, what does that look like? So the voltage plot that you should get should look like this. It should start off at 17 volts and then pretty much terminate over this time span, RC time constant. It should terminate at 2.5 seconds at a value of 24 volts. So that's basically it. Starts off at 17 and it ends up at 24 volts. That is the time response of VA. So with that being the analysis there, that is all that I'm going to cover in this particular lecture on this particular problem. So that completes all that I wanted to cover in this lecture, and hopefully it was helpful for you. Thank you for watching, and have a nice day.